Hello, I'm Cindy Kemp. Welcome to my presentation on ecosystem restoration using sUAS, Small Uncrewed Aircraft System, also known as drones. Ecosystem restoration is helping an ecosystem return to a natural, healthy state. This includes, but is not limited to, planting native trees and plants, removing invasive species, shoreline restoration, reestablishing wetlands and water flows, prescribed burns, and seed collection. Prior to 2010, drones were primarily used by government, researchers, and hobbyists. Some early innovators were Jordi Munoz and Chris Anderson, founders of 3D robotics. In the 2010s, drone use for ecology really started expanding due to dropping costs. They're primarily used for high-resolution photogrammetry, topographic mapping, and surveying. In the present day, drones are very common in ecosystem restoration with a wide range of uses. Just to name a few, habitat mapping, tracking wildlife, plant growth, and even fire progression. This is a test flight from a helicopter made by Jordi Munoz in 2008. It's created from parts hacked from a Nintendo Wii controller. Chris Anderson and his son built a UAV from a Lego Mindstorms NXT robotics kit back in May 2007. Chris and Jordy created an open source ecosystem starting with ArduPilot, an open source autopilot software suite, and then 3D robotics. The images shown are early drones created. Top left crashed on the first flight, the one in the middle was successful. Jordy didn't have the equipment needed to cook the circuit board, so he hacked a toaster oven and after some trial and error started manufacturing circuit boards and then drones. Their early boards sold for a few $100s, so they helped make drone technology affordable, which accelerated early ecological monitoring projects. There are significant advantages of using sUAS in ecosystem restoration. Low cost, access to challenging terrain, high resolution, human safety, frequency of mission, drones are rapidly available, create less disturbance, and allow for precise geolocation. Regulations follow FAA Part 107. The pilot needs to be licensed, maintain visual line of sight, fly at or below 400 feet, obtain authorization if in a controlled airspace, have remote ID, should always check temporary restrictions, get permission from landowners, and follow local regulations. What may be coming soon is the BVLOS, Beyond Visual Line of Sight, and if allowed, this would be a great benefit for surveying missions, particularly over large or challenging terrain. There are primarily three types of drones used: fixed wing, multi-rotor, and VTOL. An example of a fixed wing is an RC electric plane. An example of a multi-rotor is a DJI Mavic 3M. This one has 4 rotors. And a VTOL example is a Wingtra, and the Wingtra has a vertical takeoff and landing. Sensors that can be attached to sUAS include RGB, which capture the red, green, and blue visible light, multispectral sensors, which capture multiple bands on the electromagnetic spectrum, like RGB and near infrared, NIR. There are hyperspectral sensors, which capture data from many narrow spectral bands, some even more than 200 bands. It's very useful for species identification and determining plant health. There are thermal cameras, which capture thermal radiation. Work 247 penetrates smoke and detect hidden events like roof heat loss, and LiDAR, which transmits and receives up to 300,000 pulses per second, works 247, has high resolution, penetrates vegetation, and is quick and highly accurate. Mission planning risk factors include disturbance of local wildlife and pets if they live nearby. The weather is a big factor, battery life, communications, being able to communicate with your pilot and visual observer, and knowing the boundaries as well of private property surrounding the mission. Information products useful for ecosystem restoration include orthomosaic maps, digital surface and terrain models, multispectral indices, thermal maps and monitoring, and LiDAR mapping. I created this orthomosaic of Flint Lake from a Harper drone mission on May 2nd, 2025. The drone used was a DJI Mavic 3M using high accuracy global positioning. There were 934 images taken. An orthomosaic is very precise, so distance and area measurements can be taken. They can also be used as an overlay or background for other maps. They allow you to establish a baseline and track changes over time. This same imagery was taken back in 2024, and now they can be compared. A digital surface model provides 3D modeling of the terrain surface and all objects on it. A digital terrain model provides 3D modeling of the bare Earth surface. Digital surface and terrain models are generated from a process called structure from motion. Without going into too much detail, it uses a moving camera and two-dimensional photos. This would include photos taken from a drone as it's moving across the sky. It takes these photos and creates 3D models of an area. This video shows the two-dimensional images that were taken and the 3D model that is generated as a result. There are many indices that can be used to assess vegetation health. One of these is NDVI. It uses multispectral imagery to determine healthy vegetation versus stressed vegetation, as well as can identify drought conditions and fire risk. The colors of an NDVI image are representations of data and not natural color. Here is an example of an NDVI index. The first image is natural color of the Harper Prairie, and then there's an overlay of the NDVI image of the Harper Prairie. The overlay has colors ranging from bright green to orange. The bright green is healthy vegetation, and the yellow ranging to orange is unhealthy to no vegetation. Thermal maps can be created using data from a thermal sensor showing temperature variation. Thermal sensors can also be used to track wildlife and create population estimates. LiDAR allows you to generate a 3D point cloud and create 3D modeling. As in the video in the top right of a forest canopy, you could see the height and the structure of the forest. You could also use this to determine the biomass, which is the total amount of organic material and very useful in ecosystem restoration. Additionally, with LiDAR, you can reveal the earth beneath the vegetation cover, which is a pretty cool feature shown on the bottom right. So what can you do with all these things? Well, one is track change over time. In this example, multispectral orthomosaics below are from July and October. They allowed the assessment of the fire damage and calculation of the resulting burn scar. There's significant change that you can see resulting from this fire. You can then use those maps to calculate the size of the burn scar and determine the acreage. The sky really is the limit on what we can do with these drone sensors and data. We can implement, monitor, and manage our projects, map vegetation cover, determine species composition, health, and counts, detect invasive plants and trees, identify canopy height, do pre-burn surveys, post-fire scar monitoring, wetlands and waterways, tracking erosion and water quality, soil loss, soil quality, soil stability. We can map habitat corridors, monitor and count wildlife, detect forest fires, and this really is just the tip of the iceberg. And drones can be used for many more things related to ecosystem restoration. We can plant trees up to 30 per second, get involved in prescribed burns, dropping dragon eggs to start the fire and then monitor from above. You can drop fire suppressant balls to try to put out the fires, drop seed pods for mass planting of native plants and grasses, do pesticide applications, soil prep, soil amendments, drop soil microbes, release pollinators. Again, the list is endless. And now for the future of drones in ecosystem restoration. The first thing I think we need to mention is AI, AI, AI. With these learning modules, large data sets, and autonomous robotics all coming together at the same time, we probably can't even imagine some of the things that will be possible in the very near future. So here is a list of just a few. Autonomous robotic operations and 3D maneuvering. This would allow for mobile tracking of animals and maybe even insects within a canopy or understory. Sensor improvement year after year. We'll see more bands, finer detail, sharper resolution, super sensors combining RGB, LiDAR, hyperspectral, and thermal into one gimbal will be smaller and lighter and connected via 5 or 6G to immediately transfer these data sets. We'll see multi-robot collaboration, swarm technologies used for planting and fire monitoring. We'll see new robotics, even soil burrowing drones, event cameras. There's going to be drones triggered by an event that happens. Collection ability, seed collection, water testing, etc., and even selective spraying. The drone could go out and find and treat only individual invasive species. As you can see, there's a lot to look forward to in this industry. I appreciate your time, and here are some references if you want to take a look at some of these exciting videos and new technologies.